Videos on, face visible, not just your forehead. Let's continue with our next discussion, everyone. Videos on. Faster, guys. Videos on. Fast. Okay, let's start with the next question, guys. For the next question, given any value of n, you need to count the number of binary strings of length n with no adjacent ones. Count the number of binary strings of length n with no adjacent ones. So for n equal to 2, the answer is 3 ways or 3 strings. And n equal to 3, the answer is 8 minus 3, which is 5, right? So the strings that I marked with X, they contain adjacent ones, means one beside 2 ones are present in adjacent indices. So we should not count them. So we should not count this, this, and this. Is the question clear, everyone? Number of binary strings of length n with no adjacent ones. Please let me know if anything is not clear. Write down the question properly, completely, carefully, and then think of the different approaches that you have. Okay, observations. Please share your observations, whatever you have observed. Numbers having only one bit set count into the answer. Okay. Number of ones are less than or equal to n by 2. Oh, okay. That makes sense. Fibonacci. That is interesting. 2 power n minus number of ways which have adjacent ones. Okay. 2 power n minus 1 into 2 power n minus 2 should give the answer, right? N minus 1 into 2 power n minus 2. N minus 1 into 2 power n minus 2. How exactly did you come up with that? Considering at least one pair of 1, 1 and rest multiplying with 2 power n minus 2. Mm-hmm. There are n minus ways to put 1, 1. Yeah, that is there. So you're considering the possibility where we have 1 and 1 multiplied by 2 power n minus 2 different combinations here. How are you considering the possibility of having a 1 and 1 here? Or are you saying it is equivalent to this? It may not be equivalent to that, right? It's still 2 power n minus 2. Yeah, your solution seems pretty convincing to me. But I have this intuition that it doesn't work. Not sure exactly how. Ah, yeah, it looks pretty convincing to me. There's a case where it will fail actually. Yeah, just try it out once. Let me know if it works. But that's a very nice idea, Siddharth. I should admit, it's a very interesting idea. There can be strings with more than one pair. Prerna, he just eliminated everything which has at least one pair. So there's that. Any ith position, we can have a 0 or 1 based on that. We can take dp of I minus 1 or dp of I minus 2. Okay. Right. So I think Amrita stepped in the right direction completely, but then says keep the previous state whether it is 1 or 0. If it is 1, we can pick. We can't pick. Go to TP of I minus 12, TP of I minus 1. Yeah. So perfect, guys. So this comes from the fact that I ask you to assume that you are at any nth state or ith state, right? To start any DB problem, to start your thought process on even approaching the DB problem before you even start the 8 steps, start the 8 steps. You should know how exactly you want to approach it. And that is by assuming that you are at any ith state or nth state. So here, let's assume that you are somewhere here. Let's say this is the ith state. Let's say there are, a lot of different index positions. You're at ith index position. At ith index position, now we should think, okay, what are our options here? What are our options? This, right? 0 or 1. Two options are there. At any ith position. Let us now focus on the 0, option 0. Let's say you want to put 0 in this ith position. If you want to put 0 in the ith position, now what is the remaining subproblem? What is the remaining subproblem? Not n minus I, it is I minus 1. We don't look in the future. We don't look towards the future states. We look on past states. We look back. I minus 1 is the remaining subproblem. How many ways are there to arrange zeros and ones in these I minus 1 positions such that they are not adjacent? Then you can put a 0 here. So this doesn't care if you're ending with 0 or 1 in the I minus 1th position. Anything is fine because what you're putting at ith position is actually a 0. So it will not be adjacent for sure. There won't be an adjacent 1 for sure. But let's say that you want to put 1 in this position. Then what should be your remaining subproblem? Ends with 0. Exactly. Ends with 0. It is still I minus 1, guys. It's not I minus 2. It is still I minus 1. But you want it to end with 0. That's it. You can say it is I minus 2 also. I'll tell you how that will turn out also. I'll show you that solution also. So let's consider the fact that I want it to end with 0 for now. We'll call it solution 1 for now. In solution 2, I'll discuss what happens if you put I minus 2 and how can you put it and everything. Exactly, ending with 0 solution. So what we observed from this is which character or which number it is ending with, 0 or 1, is it matters for us to use it for the next state or not. If it is ending with 0, you can use it for both 0 and 1. But if it is ending with 1, you can only use it for 0. Because ending with 1, you cannot use it with another 1. It will become adjacent 1 there. So it matters if we are ending with 0 or 1. It means that I need now 2 DP states, right? I need to keep track of 2 different things. I need to know how many ways are there to end it with 0 and how many different ways are there to end it with 1. So dp0 of I denotes the number of ways to generate a valid string ending with 0 and dp of 1 is ending with 1. dp1 of I is ending with 1. Using these two things, now if I try to calculate dp0 of I is equal to, it will be dp0 of I is equal to will be db expression, the complete db expression. db0 I minus 1 plus db1 of I minus 1. Exactly. Perfect. So how many strings are there of length I minus 1 ending with 0? To all those strings, you can add 0 at the end. How many strings are there of length I minus 1 ending with 1? To all those strings also, you can add 0 at the end. So for strings of length I minus 1, if they're ending with 0 and ending with 1, both the type of strings, you can add 0, 1 more at the end. And what is dp1 of I? dp1 of I is equal to, perfect, exactly, dp0 of I minus 1. You should only consider those strings. You should only consider those strings of length I minus 1 which end with 0. You cannot consider those strings which are ending with 1 because you don't want them to be adjacent ones. What will be the base conditions here? Length 0 will be length 0 will be length 0 is technically not possible. So maybe that will be a bit misleading here. We'll focus on length 1. Length 1 will be not 2, dp0 of 1. That is right, Abhishek. Index value is the length, right? According to our dp state. Oh, I didn't write of length I here. Of length I. Ending with 0, only one string is there of length 1. Ending with 1, one string is there of length 1. That's right. And where is the answer? Perfect. Perfect, guys. Perfect. Length n string ending with zeros plus length n strings ending with 1. How many such strings are there? Both you will add. That is your final answer. Table size, 0 of length n plus 1. And dp1 of length n plus 1. Space optimized table size, guys. Two. Perfect. One previous state and one current state. You need to store I minus 1 and I at each position. Make a quick note of it. Then we'll see how this will evolve into our solution 2. Yeah, sure. We need endings for 0 and 1 separately because when we were thinking here that we have two options to insert at ith position, when we were considering the option to place 0, we could take all the strings of length I minus 1. But when we were trying to consider the option where we want to place a 1 in ith position, we only wanted those strings which are ending with 0 till I minus 1. So we wanted a way to separate both of them. And that's how this all started, with ending with 0 and ending with 1. Okay, now solution 2, if you observe, solution 1. dp0 of y is nothing but dp0 of I minus 1 plus dp1 of I minus 1. But dp1 of I minus 1 is nothing but dp0 of I minus 2, right? Is nothing but dp0 of I minus 2, right? If you take this dp1 calculation and substitute it here. Yes. It means that you don't need a separate dp for 0 and separate dp for 1. You can just combine both of them into the same thing and just call it dp. Then this became nothing but our Fibonacci series dp. And you know the rest of the steps. They won't be exactly the same, but very similar. dp of 1 will be 2, right? Because number of strings of length 1 are 0 and 1, which is 2 strings. So you adjust your base conditions, and I think the rest of it will be cakewalk for you. Didn't get that. You didn't get the conversion or how to do the rest of the steps. Conversion. So I substituted this equation into the dp0 equation. I substituted the dp1 value in the dp0's calculation. if dp1 of I is equal to dp0 of I minus 1, dp1 of I minus 1 is dp0 of I minus 2. Yeah, exactly. I minus 1 minus 1. And from there, we got this. You could come to this conclusion with the help of observation as well. Time and space complexity will change. Yeah, everything will change. Base condition, table size, time and space optimization, everything will change. Rest of the steps are similar to Fibonacci series steps, not similar to this. The rest of the steps will not be similar to the solution one. They'll be similar to the Fibonacci series steps that we discussed. So let me show you how we can get to this solution 2 without depending on solution 1. Let's say you did not figure out solution 1. How will you come to this solution 2? Now I get it why I always start with easy problems like Fibonacci. Yeah, you can relate it to the easier versions whenever you can. Because as the series is 1, 2, 3, 5. Exactly, Harbhajan. So one way to come to solution to conclusion is just observe observe the pattern. N equal to 2 is answer 2, then 3, then 5, then try to calculate n equal to 4. If it is 8, then most likely it is following the Fibonacci series. But how exactly is that working? I will show you how to come to the conclusion that this is Fibonacci series. Logically, I will show you that. By observation, you can come to that conclusion, yes. But logically, how do you come to that conclusion? So logically, you are saying that if you add the number of ways that you have for strings of length, like let's say I want to calculate strings of length 3, for example. So you're basically saying that if I take my strings of length 2 and strings of length 1, I will get all the strings of length 3. That's what your equation is indirectly indicating. So let's see how to come to that conclusion. So to generate non-adjacent 1 strings of length 3, what can I do? I can take all the strings of length 2 and I can simply add a 0. I can take all the strings of length 2 and I can simply add a 0 before them or after, anything is fine. Let's say I'm going with before in this discussion. Now, I cannot take all these strings of length 2 and add 1 before them because I don't know which of them will have a 1 in the beginning because we are only keeping a track of count, not individual strings. So I cannot add 1 in front of all these strings. But I can add 1, 0 in front of all these strings. In that case, I will need all the strings of length 1 in my calculation here. Because I'm adding 1, 0 instead of just adding 1. And I have all the strings of length 3 with no adjacent ones just because of this. Similarly, see how easy it will be to get length 4, guys. N equal to 4. Okay. So now all I have to do is take all the strings of length 3. Take all the strings of length 3 and put a 0 before them. Take all the strings of length 2. Exactly. And just put 1 0 before them. It's glitching a lot today for some reason. Length 2 and just put 1 0 before them. These are all possible strings of length 4 with no adjacent ones. And that is how that Fibonacci expression is coming in our calculation. Number of strings of length n minus 1 plus number of strings of length n minus 2 will help you get the number of strings of length n with no adjacent ones. Last 30 seconds. Moving ahead. To the next question. Let's say you have a let's say you have a 6-sided dice. Sorry, Vasan, do you need me to go up? Okay. Let's say you have a 6-sided dice. And you can roll it infinite number of times. You're given a value n, let's say n equal to 14. So using the rolls of a 6-sided dice, how many ways are there to get a sum of n? Means for 14, you can do 6, 6, 2. That is one way. You can do 4, 4, 4, 2. That is one way. You can do 2, 2, 2, 2, 2, 7 times. Or you can do 1, 1, 1, 1, 1, 7 times. There are a lot of ways to get a sum of 14, right? Using a 6-sided dice. You need to count all such possible ways. Did you get the question? Yes. No, explain more. Yes, yes. Okay. Okay, take a minute, write down the question properly, completely carefully, understand what exactly is being asked, and follow all the instructions I've given you till now on how to approach these kind of problems. Put yourself in nth state or ith state and see what can you do from there or how can you get there. Please wait until I ask you to share your solutions. And no, Mika, they are considered different. 662 is different from 626. Okay, observations, solutions, whatever you have. I remember, right? 1 to 6, check previous advancement positions, and maybe and add them all. Okay. Similar to Fibonacci, instead add previous 6 numbers. Similar to staircase problem. Okay. Any other observations, anyone? F at I, then dB of n minus I. Not just n minus I. Not even n minus I. For every ith tree, try picking any of 1, 2, 3, 4, 5, 6. Go to I minus picked. Okay. So all your observations are correct, guys. Let's say you are at f of 14. You can get to a sum of 14 by rolling a 1 from 13. Or I'll just write the numbers to keep it simple. By rolling a 1 from 13, or by rolling a 2 from 12, 3 from 11, and so on, 4 from 10, 5 from 9, and 6 from 8. Means if you know how many ways are there to reach all these states, from any of these states, there is only one way to reach 14. So you just have to do a summation of all these states to get the answer for number of ways to reach 14. And if you observe, there is clearly overlapping subproblems here. If I just expanded one or two of them. So 13 is dependent on 12, 11, 10, 9, 8, and 7. And 12 is dependent on 11, 10, 9, 8, 7, 6. So clearly there are overlapping subproblems here. So any dp of I here is basically storing the number of ways to reach a sum of I. How many ways are there to reach a sum of I? If we can store that in our dp, then we can use it to calculate all the states and eventually our answer. So dp of I is equal to, for all, or summation of basically j equal to 1 to 6. dp of I minus j, right? 14 minus 1, 14 minus 2, 14 minus 3, so on till 14 minus 6. If you want to handle cases like for example, 5. How many ways are there to reach 5? You can come from 4, come from 3, come from 2, come from 1. And you can also come from 0, right? By rolling 5 directly from 0. By rolling a 5 directly. From 1, you can roll 4. From 2, you can roll 3. From 3, you can roll 2. 4, you can roll 1. Means this can also fit into the same expression. If you add one condition saying that not I less than 6. dp0 equal to 1, that will be our base condition for sure. But this will go to I minus 1, I minus 2, I minus 3, I minus 4, I minus 5, I minus 6, right? Exactly. We should put a condition saying I minus j should be greater than or equal to 0. Yeah, or till j equals to I. Anything is fine. This is not division symbol, guys. This is such that symbol. We have used it before, if you remember. So do this such that I minus j is greater than or equal to 0. Then we can handle dp of 1, 2, 3, 4, 5, 6 also using the main expression itself. You don't have to write a base condition individually for them. The only base condition you would need is dp of 0 equal to 1 to help you calculate these 1, 2, 3, 4, 5, 6 values. Speak if you did not understand anything. Speak means like type. If you did not understand anything, if you want me to repeat anything, if you have any issues, please speak up. I really appreciate it if you're understanding us and when I say anything, but I know that might not be the case always. Finish the remaining steps. Table size. Oh, sorry. First, where is the answer? Table size, time complexity, space complexity, space optimized table size. Finish all these steps. Done? Just say done in the chat if you're done. Done. What is the space optimized table size, guys? Space optimized table size is 6776. 7 is the right answer. No, Samad, how is it 2? You need previous 6 states, right? To compute ith state. Exactly. 6 previous states and 1 current state. N plus 6. Time complexity is not n plus 1 or n plus 6. It is into 6, right? It will take 6 iterations for each state, which is big of n again. Six iterations for each state. Number of states into time taken to compute each state. I'm not understanding how are we computing the answer. So here the question is asking you, how many ways are there to get a sum of n? Right? And dp of I denotes how many ways are there to reach a sum of I. So if you want to know how many ways are there to reach a sum of n, all you have to do is go to dp of n instead. Which is where your answer is. Okay, that is not a convincing expression. You're eventually going there. First, you're computing for 1, then 2, then 3, and so on. You'll eventually come to n. So the way that we are coming to n, like n here is 14, is by calculating the number of ways to reach 13, number of ways to reach 12, 11, 10, and so on, right? So when you have the answer for this, you have answer for this. And this is nothing but your dp of n. Follow-up question on this. Follow-up question will be, you're given a cost array. All right, 30 seconds, last 30 seconds. That is right, Siddharth. 662 and 626 are treated separately. All right, in the follow-up question, you're given a cost array. So the cost to roll each number on the dice is given. So cost to roll a 3 is 20 units, cost to roll 2 is 17 units, and so on. Now the question is basically changed to calculate the minimum cost to reach a sum of n. Calculate the minimum cost to reach a sum of n. Let's take n equal to 14. If I roll, for example, 662, its cost would be 14, 14, 17. Whereas if I rolled, 4, maybe 5, 5, this is 18 plus 7. This is much more optimized than 662, right? And if you rolled 1, 1, 1, 7 ones, obviously the cost is going to be 12 into 7, which is way higher than any other options that we have here. So clearly, doing it in one way or the other is making a difference in the total cost incurred. And our goal is to calculate the minimum cost that you will have to incur to get to a sum of n. Oh, this is not 12 into 7. This is 12 into 14. My bad. That is right. This is 12 into 14. Take a minute, understand the question properly, carefully. Make sure you keep your videos on. Face visible. Observations? Same as previous question. Show some. We need to find cost among all the previous 60 minimum cost among this previous 60 values as into dp5. Cost of j into dp5 minus j. Start with the number having less cost. Start with the number having less cost. So start with the number having less cost. Here, let's say you're suggesting start with 4. Let's take, for example, the n that I have is something like 10. So if we start with the number with the less cost, we'll take 4, which is the cost 7, then 4 again, which has a cost 7. And then you'll take 2, which has a cost 17. So this will come to something like 31. But the optimal value for getting to a sum of 10 looks like 6 plus 4 or 5 plus 5 to be precise. Yeah, 5 plus 5, which is a cost of 9 plus 9, which is 18. Exactly. So this is what we call a greedy approach that you have taken. So a greedy approach is basically an approach where you take the local optimum at each step. So you're making a decision on what is the best now. But what we need is a global optimum here. To get the optimal answer. No, that is not required. Knapsack technique is not required over here. I mean, in one way, all DP problems are related. So maybe somehow this is related to the idea behind knapsack. But yeah, we'll get there. Eventually, we'll get there. But for this particular problem, everyone, and everyone, it is really helpful if you make a note of this as well. Understand what is a greedy approach and what is a optimal approach. Greedy is basically a local optimum. So at each position, what is the optimal value that you can get? You're selecting that. But to get the final answer, you need a global optimum. Four plus 1 plus 1, right? Yeah, that's right, Siddharth. So if we were going with the greedy approach, we should not have taken 2. We should have taken 1 plus 1, which would have been even worse. That's right. I forward min by using global variable. Still, your decisions are being taken at a local level. You will not be able to take the optimal decision if you're making a local optimum at each step. Now coming to this discussion over here, f of 14. So the cost to reach 14 is now dependent on the cost to reach 13, cost to reach 12, cost to reach 11, cost to reach 10, cost to reach 9, and cost to reach 8. So we know that there is only one way to reach f of 14 from all of these states. From f of 13, you should roll a 1 to get to 14. And here you roll 2, 3, 4, 5, 6. But now rolling a 1 now has a cost of 1. And rolling a 2 has a cost of 2, rolling a 3 has cost of 3, and so on. So it is not just the minimum of these that you have to consider now. To get the answer for f of 14, you need to consider the minimum of these. Means combined the cost to move from 12 to 14 or 13 to 14 or 11 to 14. You need to take a decision on which is the best here. Means to get the best answer for f of 14, you need the best answer for f of 13, best answer for f of 12, best answer for f of 11, and so on, right? Similarly, to get the optimal answer for f of 13, you need the optimal answer for f of 12, 11, 10, 9, 8, and so on. And when you're taking a minimum, only one such option will give you the best option, right? Similarly, one such option here will give you the best option. One such option will be giving you the best option. So what we are observing here is not only that this problem has overlapping subproblems, which is the first DP property, but it also has the second DP property, which is it also requires you to have an optimal substructure. Where optimal substructure is basically only the optimal answer for the subproblem can give the overall optimal answer. For the subproblems, only the optimal answer for the subproblems can give the overall optimal answer. If you observe this property also, then it is the second DP property, which is known as optimal substructure. So dp of I here will store the minimum cost to reach sum of n, or to reach a sum of I in this case. Min cost to reach a sum of I. So to get the answer for any dp of I, we need to get minimum for all j equal to 1 to 6. dp of I minus j, and then exactly perfect plus cost of j. It is plus, not multiplication. The minimum cost to reach till I minus j plus the cost to come from I minus j to I. Obviously, if you write such that I minus j greater than or equal to 0, then it will handle all the 1, 2, 3, 4, 5, 6 conditions as well. with the base condition being the base condition. Base condition starts with 0 here. dB of 0 equal to perfect. dB of 0 equal to 0. Because now dB of I is storing the cost. You can initialize dB of 0 to 0. And whatever cost is incurred in the remaining states, it will come from cost of j directly. Nothing else is required in your base condition. Table size, time complexity, space complexity, where is the answer, space optimization, all will remain same. Same as above. Same as above. I have a doubt. So we are choosing optimal at each sub-problem, then it's greedy. No, you are identifying that there is a structure in such a way that only the optimal answer for each sub-problem can help you calculate the optimal answer for the current problem. So local optimum is completely different. Local optimum is where you consider only the current options, where you do not consider what is the best in the previous states. Best in the previous states is where you have taken the best decision already. That, okay, if I take this, this is the best decision for me to go forward. So you have taken the optimal for all the states till there, till f of 12, all the states till f of 13. But a greedy is an approach where you're taking optimal at only this step. If we take only one, then it is greedy. Something like that. If you only consider the possibility where, you know, I will take the minimum cost at each step. So you are not considering what is the minimum cost that you can get to reach till that step. You're only considering the costs and not the previous values that you have taken. Last 30 seconds, then we'll move on to the next question, which is a very nice question. Or we'll do one thing. I'll just show you how to convert. Interesting problems come more at the end of the session. Yeah, I mean, it comes with the flow. Obviously, we'll start with the easy problems to get to that level. And yeah. So what I'm doing right now, guys, here is I'm going to show you how to solve a DB problem and how easy it is to solve a DB problem. If you're interested, please code along with me here. And you will definitely encounter a few timeouts along the way. Python. It doesn't matter here which language we use. It's just a standard code. We are not using any data structures or anything here, right? So you can write in any language and it should work properly. Okay, on popular demand, let us start with Python today. So this is the exact same problem we discussed till now. The first variation, not the optimal variation, the variation that we discussed before that. Given a standard 6-sided dice, find the number of ways to get a sum of n. I have shared the problem link in the chat already. Obviously, if you open and if you see a 404 page, it means that you are not logged into HackerRank. So you'll be able to open that link only after you're logged into the HackerRank. And let's start with Python for now. I have C# selected there earlier because I was struggling with the code which Vaishnavi shared for nearly 4 hours and I still couldn't make any progress, but hopefully I'll make some progress today. All right, so the input here is pretty straightforward, the number of test cases and each test case has a number. Should I be proud of myself? I mean, I prefer if you, what do you say, add some comments in your code so that it will be easier for me to understand exactly what is going on. Yeah, but yeah. Otherwise, it's a pretty nice logic and yeah, it's like, you know, it's a dilemma. Should we call complicated logic good or bad, right? If you understand, it's good. If you don't understand, it's not so good. That's it. All right, guys. So let's start with the coding process. So now the coding process will start with looking at your notes. Looking at your notes, we have those 8 steps, right? So now you should see how I am simply, very easily converting those 8 steps into code. And people who don't know Python also will understand the code that I'm writing in Python. This is basically a test case loop, so don't worry about this. Yeah. Now I should just read the, what do you say, input. The number n. So now once I read the input n, now let us say that I want to go with a tabulation approach to keep it simple first. I will create a DP array of size n+1. I'm initializing it to -1, but you don't have to initialize it to anything if you are using a tabulation approach, because anyway, you will override them as you move forward. DP of 0 is equal to 1. As we discussed, this is the only base condition we need, right? In the list of 8 steps, this is the base condition that we wrote. DP of 0 equal to 1. So what you should observe is how I am converting all the 8 points into code. If you understand that, then you can convert any DP problem into code. So first I'm done with my base condition here. Table size is done, base condition is done. Now I can just start with my loop for loop from I equal to 1 till I equal to n, or I less than n+1. Till I less than n+1, we will loop. Whenever you come at dp of I, now it is basically a loop inside dp of I again, right? You need to add dp of I-1 plus I-2, I-3, I-4, and so on. So I will initialize dp of I to 0, and I will write a loop for j, right? This should be j. J in range 1 to 6. I will simply add everything to I. dp of I minus j. But obviously here we are not considering that rest of the equation that we wrote, such that I minus j greater than or equal to 0. We should consider that as well, right? So maybe I'll write a condition around it to keep it simple. I can do it in other ways as well. I'll just do this for now. Only then I do this. Yeah, you could use a while as well. That would have worked as well. This is also fine. So using this, now I converted our DP expression. If you observe, this is our DP expression, right? These 4 lines of code. I converted my DP expression into code. Amruta, focus. You can play around later with your settings. Now, what do we do next? We just have to print the answer. Print dp of n. That is where our answer is, right? That is the where is the answer step that we wrote. And that's it, done. 8 steps converted to code, done. So here we missed a very important point that they asked us to print answer modulo 1 plus 7. That's why we got this extremely large value here. But that's nothing that we don't know how to handle. So we can say m equal to int of 1 plus 7. And then here you can simply say dp of I plus modulus m. And I think we are done. Range did I make a mistake? This is inclusive. I less than 7. That is right, range. Yeah, sometimes Python plays with me like this. But that's just me. You probably handle Python better. And if we submit, what do we get? Yeah, perfect. TLE. But not because of Python. I assure you that this is not because of Python. Any language you write this code, you'll get a timeout error. And what is the reason? What is the reason? What is the reason? What is the reason is our code will take t into n time. Our code will take t into n time, right? But here t is 10 power 6, 10 power 5. N is 10 power 5. So which is 10 power 10 iterations. Obviously not good. We don't want that. So what do we do? How do we optimize it here? How do we convert a t into n code into something better? Perfect. That's right. We can simply store all the answers for all possible inputs first. Then we can answer every test case in constant time. If your DP array has answers up to 10 power 5, then you don't have to calculate for anything again. So what I'm going to do here is I'm going to just rip this code from here, put it in my global scope, which is bad, I know, but let's just get on with it for now. And this will be 1, 2, 3, 4, 5, and this will be 1, 2, 3, 4, 5. It is 5 because of the input. Because of the constraints. Constraints say that it goes till 10 power 5. Because of that, we are setting this to 10 power 5. So now I have initialized with this loop. I have initialized all the input, all the indices from 0 till 10 power 5. Now I just have to print it. Run test working, submit. and accept it. Great. So we have converted a code which will take t into n time into something like n plus 3 time. You can consider 10 power 5 as n, for example. Then we have converted it to n plus 3 time. We are answering every test case in constant time. And this is how you need to solve all the remaining problems as well in dynamic programming. Most of the problems, the answer will not change from one test case to the other. If you get that number, it is most likely going to be the same answer every time. You should understand the question properly to do that. Anyway, let me just quickly show you how to write a recursive or a memoization approach here, so that your knowledge of DP is complete. Before that, any doubts here? Is this clear? How to write DP, how to optimize, how to bring it from t into n to t plus n, etc. How to convert your 8 steps into code. Any doubts? Anything you want me to reiterate on? All clear? Yes. Or anything you want me to reiterate on? Okay, I see some head nods, but better if you type. Yes, clear. Okay. Second line is not needed, right? This one. I mean, if you're trying to append, then probably it is not needed. Didn't understand array of 10 power 5 is helping there. How array of 10 power 5 is helping there? We are pre-computing all the values. So if you look at our test case, you'll understand test case loop. In our test case loop, there is no computation at all. We are just taking the answer from the array and we are printing it directly. If you understand this, then you'll understand what is going on here. Rather than test case, we can call them queries. Yeah, it now became something like that. Yes. Each one is just a query that you want to answer from the DP array. Siddharth, is your doubt clear? Did you understand what is happening here? Okay. Sorry. Yeah, n plus t. N is this, t is this. Let me show you how to write a recursive code here, guys. For recursive code, I'll just get rid of this for now. Let's just put this in a function for completion's sake. Main def function name is something like, I don't know, dice maybe. And what we'll do is we will create a DP array with -1. 1, 2. And then we'll simply say DP of 0 equal to 1. I mean, we don't even have to say this. Your base condition will probably handle it. And instead of calling DP of n over here, we'll probably call dice. Maybe we can pass the DP array over here in the parameters. All right, now I'm writing the memoization function for this. So first I'm going to handle the base conditions. Only one base condition is there. If n equal to 0, 1 is the answer. DP of 0 equal to 1. That is the only base condition that we need. Now, if DP of n is not computed, only then we compute it. Only then we compute it. Then we say DP of n equal to 0. We still need something like m equal to end of 1e9 plus 7 over here. Then this time I'll show you with a while loop maybe. Or let's just go with a for loop. For j in range 1, 7, DP of n is equal to DP of n plus, tell me guys, plus What will come here over here? Perfect. Dice of n minus j comma dp. Sorry, not this of, this of n minus j comma the dp array. Of course, you should still write that condition here. If n minus j is greater than or equal to 0, only then you do this. And then you return dp of n. Let's run and check the code. I applied. Sorry, I think I missed modulus here. Modulus m. Okay. So one thing you guys have to observe here. Look at my code once. So when you are posting in queries, I see your codes. And I don't understand why you guys apply modulus here, every single place. I just applied one place. That is more than enough. You apply here, every single place you apply. If just refer to our modular arithmetic discussion once, if you are confused. And yeah, just write some clean codes, guys. Clean codes. And if we submit, what will happen, guys? What is the verdict? What is the verdict? Verdict. Tell me, what is going to be the verdict? TLE accepted. Accepted. How is this accepted? We didn't do the pre-processing and everything here, right? Like we did for the previous problem. Here we are calling the dice function inside the test case loop. How is this working? We didn't do any pre-processing. Yeah, we did memoization. That's right. So the key here is my DP array is initialized outside my test case loop. It means that whatever answers we computed for the previous iterations, exactly, it will just reuse them in the next test cases as and when it is required. Means if the first test case you got is, for example, n equal to 10, 1 to 10 is computed. And if the next test case is 20, it will only compute from 11 to 20 because 1 to 10 is already computed. You got a TLE. You should not get a TLE. Check if you applied modulus properly. And yeah. And that's how memoization works, guys. I hope now you understand how we can convert those 8 steps into memoization code or iterative code, any code that you want. Just for the sake of completion, I will also show you the space optimized approach. But I hope by now you understand that a space optimized approach will not clear the time constraints here. Right? Space optimized approach, you will only be able to compute the current answer. You'll not be able to store all the previous answers. I mean, that is why it is space optimized, of course. So the space optimized approach is basically applying a modulus at every single place you are accessing dp of I. Modulus 7. And you will have brackets here, obviously. Okay, you can't do it in this, sorry. You should do it in the TLE version of our code. Yeah, here. This will be size 6 plus 1. 6 previous states and 1 current state. Here. Apply modulus 7. That is the space optimized size for us. And run. Done. Yeah, it will time out for sure because we are recomputing for each test case. But at least now, I hope you understand what is the difference between a regular DB expression and a space optimized DB expression. Just the table size is changing. That's it. Nothing else will change. Because table size changed, you should apply that modulus everywhere you want to access the index of that array. Any doubts? Please ask. Anyone submitted, accepted? If your code is submitted and accepted, please say done in the chat. Done. Okay, that's great. Okay, I enable mark activity, everyone. The second mark activity, please mark it. Second mark activity has been enabled, everyone. Please mark it. The second mark activity has been enabled. Please mark it. And let's talk about tomorrow's contest once. You forgot, right? No? Okay, great. Let me explain the memoization in recursive code. So because our DP is persistent, and because we initialize everything to -1, if dB of n is -1, it means it is not computed. Only then we are computing it. So these 4 lines of code that we have, that I have highlighted here, this is basically adding dp of I-1, I-2, I-3, and so on, and storing it in dp of n. Yeah, just like Fibonacci series. But here the only thing difference is Fibonacci series is just I-1 and I-2. You didn't need a loop. Here we need a loop because it is going up to 6. All right. Now regarding tomorrow's contest, guys. Tomorrow's contest is going to be a medium hard contest. Although I will say it is more towards medium, less towards hard. I did not give you any tree problems. Although there is one problem you could probably solve using trees, but you can solve it in other ways as well. And the theme of that contest is basically or topics that you need for the contest are basically just, arrays, searching, maps, sorting, sets, basic string matching algorithms. That's it. So this contest is more oriented towards you coming up with new approaches and solutions, and less towards what we discussed applying in the contest. So the relation with the content versus the contest is a bit more abstract. It's not direct. But for the previous contest, if you remember, it's a bit more direct. So the problems that we have in